Hello everyone. For this tutorial video, I would like to show applications of reflection and refraction of light, starting with something known as total internal reflection, and its application in electronics such as fiber optics. As you may already be able to envision based on what we saw with the pencil in the water in the last video, physical mediums will not either reflect or refract, but rather will do both at the same time. So we would have to take that into account when we solve problems related to that. And in particular, we would have three angles now, where angle 1 is the original ray entering the surface, angle 2 is the reflection, and angle 3 is the bending or refraction. If we think carefully about how refraction works, we can see that if the index of refraction for the second medium is less than the first, the ray of light will bend away relative to the perpendicular line the angle is measured from, since we remember from Snell's law equation that if the index of refraction is greater, the angle must be greater too. If we were to increase the angle of attack of the original ray, we would see the angle of refraction must increase as well by this law. And because of how refraction works, i.e. the bending or changing of the light's path, it follows the largest the angle can be is 90 degrees, because anything greater than 90 would be on the same relative side as the original ray, and so therefore would no longer count as a refraction. Because of this special limit, there is a technical name called the critical angle, which is the angle of the original ray required to make a refraction of 90 degrees. Because we remember that if the angle of refraction is greater than 90, it will be on the same side as the original ray, it would follow that this would add to the reflection, and as a result, the technical term for this is total internal reflection, as a reference to the fact that all of the angles add up to a reflection. Since we remember that Snell's law of refraction is index of refraction at point 1 times sine of angle at point 1 equals index of refraction at point 2 times sine of angle at point 2, we can see that at the critical angle, i.e. the angle when the refraction is 90 degrees, that index of refraction times sine of angle 1 equals index of refraction 2, end of story, because sine of 90 degrees equals 1. Which we can see visually why, using right triangles, just like we saw visually why cosine of 90 is 0. So next, we algebraically rearrange the equation so that the sine of the critical angle that is equal to 1 is equal to the sine of the index of refraction at point 2 divided by the index of refraction at point 1. And so, we would simply take the inverse sine of both sides. And we have a convenient formula that we can use on the fly to figure out the critical angle for when total internal reflection occurs. For example, in a plastic fiber optic cable such as this, we would look up the index of refraction for the material, which depends on the type of material, but I will use an arbitrary number just to demonstrate an example, so we will make an assumption that the index of refraction of this material is 1.49. And since we know from looking at it visually that the other medium the refraction is occurring at is air, that we assume its index of refraction is 1, or the index of refraction in a vacuum, and so we would plug in this ratio and figure out the inverse sine of it, which gives us 42.2 degrees. This means that any ray of light that enters at an angle greater than 42.2 would be internally reflected rather than refracted through. It is useful to trap rays of light like this, because we remember that the speed of light is the fastest speed in the universe, so it would be faster through fiber optic cables too, than something like regular electricity. Another thing to notice about fiber optic applications, however, is that if two fiber optic cables are in contact with each other, there would have to be a separate material called a cladding. so that the light does not literally pass straight through, but instead gets reflected back into the cable. Another application of total internal reflection that is more used mostly for aesthetic purposes rather than practical ones is the sparkliness you see in diamonds. Because we can calculate the critical angle for a diamond is 24.4 degrees, with reference to when we compare the diamond to air. If we look at the geometric angles inside the diamond, we can see that the light will only be able to exit at specific places, because of the fact the angle would have to be less than 24.4 degrees. So you would see that sparkly look only at the particular angles where the light is able to exit. Another property of diamonds, if you look closely, is that they have many colors coming out of them, even though the surface itself is technically colorless. So we will investigate why this works in the next video, under the process known as dispersion. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.